I saw that you did your graduate work at Cambridge with Stephen Hawking. And a few weeks ago, I actually spoke with another of Hawking's students, Thomas Hertog, about their work on quantum cosmology. He recently had a book that came out all about this. But since I believe, and Wikipedia has gotten me in trouble on a couple of occasions, that you did your dissertation on a different topic, and that's wormholes. I thought we might start with that since they've never come up on the show before. And most people are familiar with wormholes from science fiction books and movies, but where do they actually arise as a real tractable problem to work on in physics?
There are two types of wormhole. It's slightly confusing because you draw the same picture on a piece of paper to illustrate them both, but they differ in dimension. So one sort of wormhole is a wormhole in space, which is it connects one region of space. It's like a shortcut from one region of space to another region of space. You just go down the wormhole in one end and you pop out somewhere else in space, somewhere else. And those, it's interesting that the first instance of such a wormhole is already there, inherent in the space-time that we use to describe black holes. So, and there the wormhole goes by the rather grand sounding title of Einstein-Rosen bridge. And it connects not two regions in the same space, but two different copies of space. So one universe and another universe, they're joined by this so-called Einstein-Rosen bridge. And the interesting thing there is that in that space-time, it's the Schwarzschild space-time. It's the space-time that describes the simplest possible black hole, one with just mass and no other attributes. It's not traversable, so it's there in the description of the space-time. There's this bridge, but if you try and go down it, then it pinches off, and you actually hit the singularity before you're able to go through into the other universe. So that's a non-traversable wormhole. And people have speculated about whether there are traversable wormholes in the world and how you could keep the wormhole open long enough for you to actually get through it from one end to the other end. And people a lot of work has gone into doing that. And I would say that probably, you'd need a certain slightly exotic sort of quantum matter in order to do that. And it's not, I would say it's still an open question whether such things exist in our real universe. So that's one type of wormhole. So the second type of wormhole are wormholes in space-time. So they arise, well, speculatively, Stephen was interested in wormholes because he thought that might be what was happening when a black hole forms and then evaporates. And people asked the question, or he posed the question, what happens to the stuff that falls in? And one speculative answer to that he proposed is that, well, a little baby universe pinches off our universe and goes off and carries the stuff that fell into the black hole away with it. And that process of this baby universe pinching off, if you look at it in space-time, so if you look at the whole history of that process, it looks like a wormhole. It's not the same dimensionality of wormhole as the Einstein-Rosen bridge, but the picture that you draw looks the same, but it's just one dimension higher, one dimension up. And that proposal of whether or not this could help resolve the so-called black hole information loss paradox or puzzle was what I was working on for my PhD.
Hmm. For the Einstein-Rosen bridge, is that the same Rosen of Einstein-Podolsky-Rosen? Because that paper has come up a number of times on the show.
Yeah, so there's a sort of almost a joke kind of, but not a joke because serious people take it seriously, connection between those things because, and there's even a title of a paper, EPR, as in Einstein-Podolsky-Rosen, equals ER, as in Einstein-Rosen bridge. So that somehow these wormholes in space could have something to say or something to do with the non-locality
Right.
of physics as revealed by the EPR type correlation. So I'm hugely skeptical of that, but that is a thing.
Yeah, that's interesting. If two particles separated by some great distance interacted with one another through an Einstein-Rosen bridge, would that be considered a local interaction because nothing's moving faster than the speed of light, even though they're obviously quite distant?
What was it that it's semantics? I mean, the term local, both terms, local and causal, are so overused and used differently in different contexts, and different people can mean different things by local, and the same person can mean different things by local depending on the time of day or what they had for breakfast. So it's
Sure. I guess I just have the sense that Einstein wouldn't qualify as the sort of spooky action at a distance that he really despised if there were this wormhole connecting them and nothing was moving faster than the speed of light.
I don't know. I don't know what he would have thought about that actually. So yeah, what to say?
Yeah, I probably shouldn't be supposing I have any insight into his thinking. But one last question about these two varieties of wormhole. So the Einstein-Rosen bridge and then the baby universe pinching off. Maybe this is presaging our talk about causal sets as a theory of quantum gravity. But is the Einstein-Rosen bridge something that arises just within general relativity, or does it also importantly involve quantum mechanics? Because you did mention that I think you said this, making a traversable wormhole would require some sort of exotic quantum matter.
Yeah. I think largely discussions of Einstein-Rosen bridges, those sorts of wormholes in space, they take place within what people usually call semi-classical gravity, meaning that space-time is supposed to be in this regime well described by a differentiable manifold with a Lorentzian metric, so sort of a la GR. And then matter is allowed to be quantum. And you may or may not consider back reaction from the quantum matter onto the space-time. And if you want to keep a wormhole apart, traversable, then you would have to consider the back reaction of this rather exotic matter with negative energy. You'd have to consider the interaction between that quantum matter and the semi-classical, the differentiable manifold structure of space-time. So that's different from what people mean when they say full quantum gravity, where there are sort of fully quantum effects of space-time itself that can't be described by a differentiable manifold with a Lorentzian metric. So yeah, so the sort of baby universe type wormholes, they're described they arise in descriptions of the full theory or approaches to quantum gravity which are tackling the full problem of quantum gravity rather than just space-time as we know it, but reacting to behaving as if the matter in it is quantum. So, but there's overlap, and some people who are thinking about the baby universe type wormholes are thinking about them as in some sense semi-classical. So there's that's not a hard and fast rule, but that typically, yeah.